Hi. Now in this example we have to calculate the mean for a normal distribution. So if you haven't done this already, just pause the video, come back when ready and I'll run through the solution. Okay, let's see how you got on if you had a go. Well, we've got the heights of an adult female population are normally distributed with mean of 162 centimeters. And now we're told that the heights of an adult male population are normally distributed with standard deviation of 9 centimeters. And given that 90% of adult males are taller than the mean height of adult females, what we've got to do is now find the mean height of an adult male. Well, first of all, what I want to do is define the random variable, let's say x, which will be the height of a male. So if we define that first of all, let x be the random variable, height of a male measured in centimeters, where x is distributed normally with a mean of mu and the variance will be the standard deviation squared. So the variance will be 9.0 all squared. Next, as usual, I'd want to draw these two graphs, one of x and then one for the standardized normal distribution z, directly below one another. Okay, so on this one here for x we're trying to find out the mean mu. What we know though is that the heights, we're told, given that 90% of adult males are taller than the mean height of adult females, that's 90% are more than 162 centimeters. So where's 162 going to be on this graph here? Well, it's got to be to the left of mu, because the chances of getting someone more than 162 centimeters is 90%. So we could shade that part in. That's 90%, or 0.9. Let's just mark that in there, 0.9. And obviously that means that this area at this end must be 10%, or 0.1. Now what we normally do is we project a line down from the normal distribution for the random variable x down onto the standardized distribution. Remember, the mean for this is 0 and we're trying to find out what this value of z is. Again, the probability of being more than this z value, this particular z value, is 90%, or 0.9, and the probability of being less than it is going to be 0.1. And we know that, let's just draw a line down there, we know that any observed value z is always equal to the observed value up here, let's call it little x, minus the mean mu all over the standard deviation sigma. So if I'm trying to work out mu, I know x, it's the 162, I know the standard deviation, it's 9. What I don't have is what the corresponding z value here is going to be. So how do we get that? Well, we just use our tables. And we've got two sets of tables that we can use. And first of all, I would want to look in the inverse normal tables, and here's an extract from them. Remember that these tables give us the probability of being more than a particular z value. And you can see on this graph here it's represented by p. And so that would mean that if I was using these tables, we've got a slight problem here, because this area here given by p is always less than 0.5 generally for these tables. Well, I can use the principle that we know it's 0.1 at this end, but if I mirrored it across to the other side here, then and I looked at 0.1 for p at this end, whatever z value I get here would be here, I just have to negate it. So I hope you follow that. Okay, so what I'm saying is that if P has an area of 0.1, which is this value here, then the corresponding Z value would have been 1.2816. That would have been the Z value here. But now I just mirror it over the other side and it becomes minus 1.2816. Okay, so we could say then that this Z value here is minus 1.2816, and that equals the observed value 162 minus the mean, which we're trying to find out, divided by the standard deviation, which is 9. Now you don't have to use these tables. You could use just the normal tables which give you the probability of being less than a value of Z, okay, when Z is on the right here. So again, if we were doing this, we've got a slight problem because Z is on the left here. But again, if I mirror this over to the other side, then the area to the left of Z, if I put it here, would be 0.9. So if I was to look up 0.9 for this probability, okay, in a set of tables like this, you'll notice we have to look down this column here. I haven't got 0.9, but I can get as close as I can to 0.9, which is this value here, 0.8997, and the corresponding Z value is 1.28. Now that would mean that this value here for Z would be 1.28, but if I mirror it back over to this side, it'll be minus 1.28, which corresponds fairly well to the value we've got here. So it's up to you which set of tables you use. Normally there's some kind of error margin that they build into the mark schemes for something like this, okay? So all we need to do now is just essentially solve this equation. So I'm going to multiply both sides by 9, and then I'm going to add 9 times 1.2816 to both sides. So rearranging this, we would end up with mu equaling 162 then plus 9 times 1.2816. Alright, work that out, and what do you get? You get 173.5344. And if we give this, say, to 3 significant figures, then this will be 174 centimeters to 3 significant figures, 3 SF. And it does help to have your diagrams, as I've generally always pointed out in questions like this, because you can do checks where you can see that mu has to be a number more than 162. I find it so easy that you can make mistakes with things like this. Students do make mistakes. I make mistakes where we forget a minus sign and it leads to errors, but at least we can see by drawing the diagram whether our answers seem plausible. Alright? Okay, well that brings us now to the end of this particular video, and hope that it's been of some use to you.